A wolf has appeared. Or rather, that's what the alarm said. Let's put a familiar fable back on trial today. Not in the court of morality, but in the court of mathematics. A bored boy cries wolf, and each time the villagers run up the hill. After so many wasted trips, a real wolf finally comes. But this time no one believes the boy. For more than 2,000 years, this story has been read as a lesson in the price of lying. But even if the boy had been perfectly honest, without telling a single lie, the village might have met almost the same fate. Imagine instead an honest but imperfect watchman who sometimes mistakes wind-blown bushes or a stray dog's shadow for a wolf. In this village, a wolf comes down about one night out of every 100. He watches diligently and sounds the alarm every single night a wolf comes. But on about 1 out of every 20 peaceful nights, he sees something that is not there and sounds the alarm. And just now that alarm sounded. What is the probability that there really is a wolf on the hill right now? It catches every wolf and makes a mistake only 5% of the time, so it feels almost certain. Before we calculate, lock in an answer. Soon we'll measure just how far your intuition missed. In most minds, the calculation is over in an instant. If there is a 5% chance the alarm is wrong, then there must be a 95% chance the alarm we just heard is right. The answer is not 95%. Remarkably, it is less than 17%. Of every 6 alarms, only 1 means a real wolf. The other 5 are false. This intuition is not wrong because it is foolish. A normally useful shortcut has walked into a conditional probability trap. A 5% false positive rate means that, given 100 peaceful nights, the alarm sounds falsely on 5 of them. But what we want is the probability that tonight is peaceful, given that the alarm has already sounded. The two statements look like mirror images, but the condition and the outcome have traded places. In conditional probability, you cannot swap the two sides of the vertical bar at will. This is not something to settle by arguing over words. When probabilities look suspicious, count every case. Now let's gather 10,000 nights in the village and spread them out as a stack of monitoring logs. 10,000 nights spans about 27 years. That is a long stretch, but the calculation still takes only the 3 conditions from the opening. Wolf nights make up 1% of the total, so there are exactly 100 of them. Sensitivity is 100%, so the alarm sounds all 100 times. These are the true alarms. The remaining 9,900 nights are peaceful. Even if it cries wolf on just 5% of those nights, that still creates 495 false alarms. The alarm sounds 595 times in all. 100 true alarms plus 495 false alarms. Today's key move is to ignore all 10,000 nights and isolate only the 595 times the alarm sounded. Of those alarms, only 100 actually came from nights with a wolf. In the end, only 16.8% are real, or about 1 in 6. Now let's lay out the same calculation in a single picture. The 100 red dots on the calendar at left are wolf nights. Across 10,000 squares, they are only a rare scattering. The yellow dots are 495 false alarms. There are almost 5 times as many as the real ones. The bar at upper right is the engine room of the paradox. There are 9,900 peaceful nights, but only 100 wolf nights. 5% is a small rate, but the group it is applied to contains 9,900 peaceful nights. True alarms, by contrast, can never exceed the 100 wolf nights, no matter how perfect the detector is. True alarms have a low ceiling. False alarms have a vast reservoir. Every peaceful night. That is why the roster of 595 alarms at lower right becomes a yellow ledger in which 83.2% are false. The battle over what an alarm means is fought not on a performance chart, but in the head counts of the target and everyone else. So why not just reduce the false positive rate? Let's find exactly how low it needs to go. We'll hold the wolf's base rate and sensitivity steady, and slowly turn down only the false positive rate. True alarms are pinned at 100, so the turning point is where false alarms fall below 100. Let's see where the yellow line meets the red ceiling. At our village's 5% false positive rate, there are 495 false alarms, and only 16.8% of all alarms are real. Cut the false positive rate five-fold, down to 1%, and false alarms fall to 99%. Yet the alarm's reliability is only 50.3%, barely better than a coin toss. The false positive rate must fall to 0.1%, or 1 in every 1,000 peaceful nights, for false alarms to drop to 9.9%. Only then are 91% of its alarms real. The fateful point where the two lines meet is a false positive rate of 1.01%. When the target base rate is 1%, the false positive rate must fall below roughly 1% before most alarms are real. This mismatch, where the test itself is excellent yet most positive calls are wrong, is the false positive paradox. Now let P be the target base rate, S the sensitivity, and F the false positive rate. T stands for target, and A for alarm. The probability that an alarm is real is the true alarm share divided by the sum of the true and false alarm shares. In the numerator, S times P is the true alarm share. In the denominator, F times 1 minus P is the false alarm share. In our village, P is 0.01, S is 1, and F is 0.05. That gives a true alarm share of 0.01 and a false alarm share of 0.0495. For most alarms to be real, the true alarm share must be greater than the false alarm share. When S is 1 and P is 0.01, F must be less than 1 over 99. When the target is very rare and sensitivity is close to 1, this condition simplifies to roughly, F must be less than P. The probability formula behind this rule is Bayes' theorem. It tells us how to update an old belief when new evidence arrives. This tug-of-war is not confined to a village in a fable. Every watchtower searching for something rare is pulling on the same rope. Passengers carrying dangerous items through airport security are exceptionally rare. Belt buckles, coins, and key rings, on the other hand, are common. So most beeps come from objects that are not dangerous. Airports know this arithmetic. That is why the first alarm is not an order to arrest someone but a question. Should we take another look? A kitchen smoke alarm is similar. Real fires are rare, but cooking smoke is common. We still put these noisy machines on our ceilings because the cost of missing a single real fire is far greater. In statistics, labeling something harmless as dangerous is a false positive, also called a type 1 error. Conversely, missing a real danger is a false negative or a type 2 error. Lower the decision threshold and misses decrease, but false alarms increase. Raise it and the reverse happens. So the first question in alarm design is not, how accurate is it? It is, which kind of failure costs more? Spam filters reverse the pattern. Messages sent to the spam folder usually really are spam. That is because the target spam is not rare. When the target is common, the field tilts toward true positives. In machine learning, the share of alerts that are true is called precision. Put all 4 settings on the same scale, and you can see how sharply target rarity divides their outcomes. Using the rough benchmark values here, fewer than 0.1% of airport security alarms are real, while only 9% of rare disease screening positives are real. The share of true alerts is 16.8% in the boys' village, but reaches 99.2% in a spam filter, where the target is common. These 4 figures are rough values for building intuition, but they are all members of the same family, born from the same Bayesian formula. In medicine, the rate at which a test correctly identifies patients is called sensitivity. The rate at which a test correctly clears healthy people is called specificity. It is 1 minus the false positive rate. And the share of positive results that come from real patients is the positive predictive value, or PPV. Even a test with 99% sensitivity and 99% specificity can, when prevalence is 0.1%, have a positive predictive value as low as 9%. The false positive paradox tells the story from the alarm system's side. Base rate neglect tells it from the mind holding the result. Now let's turn all 3 dials at once. Target base rate, false positive rate, and sensitivity. The first dial is the target base rate, P. It sets how common the thing we are looking for, such as a wolf or a patient, is in the world. The second is the false positive rate. It controls how freely alarms slip through when no target is present. The third is sensitivity. It is the share of targets the system actually catches when they appear. Our 4 presets are the boys' village, airport security, rare disease screening, and a spam filter. In our village, even raising sensitivity from 70% to 100% moves PPV, only from 12.4% to 16.8%. When rare targets and false alarms dominate, as they do here, reducing the false positive rate moves the needle far more than raising sensitivity. When choosing a tool to find something rare, ask not only how well it catches the target, but also how often it flags something harmless. Now let's return to the original fable and reconsider why the villagers stopped listening. If each cry has a reliability of 16.8%, then about 5 out of every 6 times the villagers drop their tools and run up the hill, they make the trip for nothing. The best response depends on the cost of mobilizing and the cost of missing a wolf. Still, learning to trust an alarm less after repeated false alarms is perfectly natural. Today, this growing numbness has a name: alarm fatigue. Hospital monitors, car alarms, and the flood of alerts in security control rooms all carry the same problem. The more sensitively a system is tuned to avoid misses, the more false alarms it creates. And the more false alarms people hear, the more likely they are to mute or ignore them. It is a tragedy in which the effort not to miss anything ultimately causes misses, and sensitivity breeds numbness. The first solution is to turn an alarm into a question, not a command. Just as a checkpoint beep leads to a bag search, reserve major action for signals that pass a cheap, fast second check. Each time a signal passes a discriminating confirmation step, the target's base rate rises within the remaining group, and the next alarm carries more weight. The second principle is to tackle the false positive rate first when the target is rare. The outcome might have changed if, after the boy's cry, a single watchman in a tower had first checked the hill. What the boy needed was not a punishment, but a second filter whose errors did not perfectly overlap the first. As we walk back down the hill, let's sum up today's verdict in 3 sentences. First, in our village, the wolf base rate P is 1%, sensitivity S is 100%, and the false positive rate F is 5%. The alarm's PPV is 16.8%. Second, true alarms have a ceiling set by the target count, while false alarms have a reservoir containing everyone else. So for an alarm about a rare target to become trustworthy, its false positive rate must fall to roughly the target's base rate. Third, airports, hospitals, spam folders, and the village all obey the same formula, yet target rarity gives them different fates. An alarm system's performance comes from the factory, but the weight of a single alarm comes from the world where that system operates. The boy who cried wolf was not a liar. He was simply an overly diligent alarm system watching for an extremely rare wolf. If you enjoyed today's video, please subscribe, hit like, and turn on notifications. I'll see you in the next story.